Okay, so we are in chapter 7, and we're going to wrap up chapter 7 today. Just so you look ahead for this week, on Wednesday we're going to do a little final exam review, and we'll try and tell you more about the final exam on Wednesday. Okay, and then of course you probably know already, but your final is a week from Wednesday, whatever it is, 11:30 to 1:30, I think it is. My office hours are posted on the Blackboard website for next week, so you can check that out if you need to come by the office. And just a quick summary where we left off last time. As I told you before, the first half of chapter 7 talks about the drag forces over a flat plate and the friction coefficient and the shear stress on a flat plate. We could have totally laminar flow, we could have totally turbulent flow, or mixed flow. So then we, after the flat plate problem, we jumped over to other geometries. We looked at a cylinder, and I mentioned that the sphere behaves similar to a cylinder as far as the drag coefficients on it. So we talked about this graph last time. It's the drag coefficient C sub D as a function of the Reynolds number. We use the drag coefficient C sub D to get the drag force on the cylinder or sphere. This is a sphere. The figure number's in the textbook there. It behaves rather strangely, depending on the flow pattern, very complex. And you have the pictures in your notes about different regions, what happens here, what happens here, what happens over here. We did different A, B, C, D sketches of what's going on. But just to look at the major difference there in the two is if we looked at this region here, call that region 1 and call that region 2. Well, region 1 can be when the flow approaches there's a stagnation streamline. The flow goes around the cylinder or the sphere. It separates at a particular location. Once the boundary layer separates from the surface, we develop a very large wake region behind the sphere. So it looks something like this. And that creates considerable drag. That large wake region creates drag, and of course the velocity approaching here is u. That's where we are here, okay? Then what causes the drag coefficient to drop? And not just by 5 or 10%. No, look at 0.5 down to close to 0.1. That's a significant drop in C sub D. Okay. Well, 2, here's the second picture. At a certain Reynolds number, something happens to the flow. The flow starts out with a boundary layer, and this is a laminar boundary layer. And so laminar boundary layer, the Reynolds number calculated, and if it gets to that range, what happens is the boundary layer transits to a turbulent boundary layer, and because of the increased momentum close to the surface of the sphere, it sticks to the sphere's surface longer. And it causes the wake region to be much smaller than it was before that transition to turbulent flow occurred. So now, because there's a smaller wake region, there's a smaller drag on it, and the C sub D drops off rather dramatically quickly. It recovers and slowly gets back up again, but there's a tremendous drop off in that region right there. And of course, we use the C sub D to calculate the drag force. So F sub D C sub D times the area rho v squared over 2. What's the area? The projected area of what you see. If I see a sphere, what I see as an area is a circle, pi d squared divided by 4. That's what goes in there. Of course, in this case here where I would increase the velocity to get a bigger Reynolds number, that guy's squared. Don't think the drag force, it drops rather fast. But don't forget too, the velocity, if we're changing the velocity in the wind tunnel, if this is in a wind tunnel, if we change the velocity in the wind tunnel, then that's squared. So that's big, okay? So we're not plotting the drag force. We're plotting the drag coefficient, C sub d. Okay, so I'm going to blow this up now because I'm going to show you how roughness affects this. What if the sphere becomes rougher? So I'm going to take from 10 to the 4th to 10 to the 6th. Okay, I'm going to take this region right in here. I'm going to blow that up over here. Okay, so here is the region from 10 to the 4th to 10 to the 6th. Is Reynolds number based on diameter. And C sub d, by the way, that was a log-log plot, of course. I plot this now on a rectangular paper, so it's 0 to 0.6 roughly. So 0, 0.1, 0.2, 0.3, 4, 5, and a little more, 0.6. And so this guy here transits roughly around 4 times 10 to the 5th, this sudden drop. So it's 0.5 out to about 4 times 10 to the 5th, right about here. So it comes over here fairly flat. It goes up a little bit. And then at this point, it drops real fast down to about 0.05. And then it recovers like that. So that's the same picture that's over there, but just blown up to a larger scale. Now, as the sphere gets rougher, the rougher creates turbulence. Roughness does that, creates turbulence. So now we have more turbulence in this region here. That increased turbulence causes the boundary layer to stick longer there. And so now it drops off at about 4 times 10 to the 3. 4 times 10 to the 3, right about there. So it's up here, and now it drops off like this, down to about 0.24. Like this, and then it pretty much stays there out that way. What happens is that sudden drop in C sub d, which occurred here at about 4 times 10 to the 5th, now it occurs down here at roughly 4 times 10 to the 4th. So this is rough. Rough surface. This one is a smooth surface. So by roughening the surface, you at Reynolds number 10 to the 5th, a smooth one, C sub d 0.5. A rough sphere, 0.24, half of that, half of that. You decrease it by 50%. So why is that important? Well, it depends. Maybe you like to play golf. Okay? There's dimples on a golf ball. What are those dimples like? They're like roughness on the surface. I don't feel it's not smooth. Definitely not smooth, I guarantee you that. It's rough. Well, this is the curve for a golf ball. Right here, that's it. That's how it behaves. So, this is a golf ball. You want to hit a smooth golf ball? This is what the books say. They actually took a lot of golfers and gave them smooth golf balls and said, hit these things, please. And they averaged how much their distance was. That's what they did, okay. Smooth golf ball, 125 yards. Dimple golf ball. Uh, 215 yards. It's not insignificant. It's not 5 to 10%. Oh, no, no. How about 90% further? Yeah, right. And so that's how it's 72%. It was not 90, 72% increase. So yeah, the dimples, what do the dimples do? They make it rougher. And the picture in the textbook, there's another curve that comes down here for not quite as rough, and one here, not quite as rough, almost smooth down here. There's different curves on there. Just like on the Moody chart, there's different curves for different roughness, the relative roughness, E over D. So that graph is in the textbook, okay? It's just not labeled golf ball. I think it might be. Okay. Let's see where we are in Reynolds number. So we have, let's do our U times, let's do it this way. That's probably the easiest. Diameter of a golf ball is 1.69 inches. Divide it by 12, get it in feet. The average hit off tee. Oh, somewhere around 100 miles per hour to, let's see what we have for the other one. Oh, there it is. 184 miles per hour. Okay. That's probably me, okay. Okay. I was watching the PGA 2 weeks ago, Tiger's last tournament, and the announcer said, whoa, did he get that ball really good? This is what he said, okay. He said, he hit that ball really good off the tee. He got 184 miles an hour off the tee. That's Tiger 2 weeks ago, okay. The average PGA, 175, just so you can see, we're close. So, get the Reynolds number. Can vary anywhere from 1.3 times 10 to the 5th to a Reynolds number 1.9 times 10 to the 5th. That's me. That's PGA. That's Tiger's number. Okay. Let's go to the graph. If the golf ball would have been smooth, 1.3 times 10 to the 5th. 10 to the 5th. Here's 1. Here's 2. If it would have been smooth, C sub D, 0.5. But since it's roughened with dimples, C sub D, 0.24. That's me. Here's the PGA guys. PGA guys, 1.9. Oh my gosh, PGA guy, he's right there. That's his C sub D. That's my C. We have the same C sub D. I feel pretty good about myself. Now, the only problem is he's hitting it with the twice the velocity I do. So guess what? When you square it, okay, when you square it, that's the difference there. Okay, so yeah, they do, but they hit it far. They hit it really far. So what now? Why? Because the dimples cause turbulence. I told you, if you got a flat plate, and if it starts off, the fan's down there blowing against the flat plate, it starts off laminar. It'll transist somewhere down here at X sub C, critical X, it'll transist to turbulent. But if I put a piece of sandpaper on this lip at X equals 0, as soon as the air hits the sandpaper, boom, turbulent. As soon as the air hits the dimples in the ball, boom, turbulent. It would have been up here, this picture, but because the dimples, it goes to turbulent. That's what causes this, okay? So, yeah, it's interesting that way, that that's why golf balls are dimpled. Now, you can also, I'll show you this. Here's articles on this. This stuff is pretty interesting stuff. Okay, here's articles. Some of these articles come out of engineering journals, okay? This one was in a golf magazine, this front page. Trying to explain to people why their golf balls are dimpled. It's kind of hard without going through the stuff ME312. That's okay. And you can see the picture on the right-hand side, the lower, looks a lot like mine. Boundary layer, wake region, drag force. Just below that picture it says, the total dimple coverage used to be 65% of the ball surface area. Now it's at least 80% of the ball surface area. So more dimples cover the ball surface. And they talk about it, about the smooth ball and then the roughened ball, and they try and walk your way through it. The larger the wake, the more drag force on a boat. Yeah, we know that. Same with the ball. Smooth ball, large wake. Then you go on the backside, what I've got highlighted there. The goal of scientists who design golf balls is to tighten the wake in the air. Tighten the wake in the air. If the air sticks close to the ball's surface, it keeps the ball airborne longer. What does tighten mean? It means you reduce the wake. This is a big wake. You tighten it down to a small wake, and that reduces the C sub D. They continue. How many are too many? Just because aerodynamic experts in research labs have found that dimples are critical to a golf ball's performance doesn't mean putting 1,562 of them on the ball will make it carry over the Hoover Dam. Diminishing returns comes at about 500 dimples, experts say, and 300 is the unofficial minimum for optimum performance. You'll find the range of 350 to 450 dimples on most golf balls. They can be arranged in a variety of shapes, most round, but some hexagonal, some shallower, some deeper. And they're clustered on the ball sometimes. As always, it says try about different dimple designs. Who do you think does that? The guys in graphic design? The guys in accounting? No, I'll tell you. I'll tell you. It's done by us and aerospace engineers, MEs and aerospace engineers. That's who does it. Who hires, all these companies that make golf balls and golf clubs hire us. Thank you very much, guys. We appreciate that. We love that. We've had guys do senior projects with Callaway golf clubs down in San Diego County because they wanted our seniors to do some work on designing golf clubs. So yeah, that's done by these people. Then, this article here, soccer ball. Oh yeah, they do crazy things. They do a corner kick, and that ball just swings around there and boom, into the net. on purpose, not because they hit it wrong, on purpose. Well, they're trying to analyze a new design. There was a new design here for a soccer ball. So some of the Caltech students said, yeah, let's try and test this thing in a wind tunnel. So they put the soccer ball in a wind tunnel and they have smoke in there. Typically, you drip oil on a hot wire, put a current through it, drip oil on it, create smoke. You blow the smoke over the ball. There it is. Look at the back side of the ball. Look where it separates, the separation point. Beautifully visible. Right there. There it is. And then the back of the ball, big region, wake region. They did studies on that because they changed the ball design for the tournaments. And they found out, yeah, there's a difference in that. Are the seams as deep as they were before? Are those different areas changed a little bit? That'll change how the ball performs and how the players have to kick that ball differently with different ball designs. Oh, there's a ton of stuff in there, just a ton of stuff in there. You can read it here about what it is, about the dimpling on golf balls again, but then they talk about the soccer ball. And you can go to the last page. University of Bath in Great Britain. University of Bath. I highlight it, but read the first few words. The University of Bath became one of the first UK schools to offer an undergraduate degree in sports engineering. Wow. A degree in sports engineering. Initially 8 students enrolled, but it grew quite a bit after that, you know. But then you can see my arrow there. It says, most of the programs are built around a core cluster of mechanical engineering courses. So the sports engineering degree is pretty much mechanical engineering with a certain emphasis on it. It says some instructors call sports engineering an emerging subset of mechanical engineering. The graduate is really a mechanical engineering graduate with a slightly different badge on. It's made interesting because they work on sports applications all the way through instead of airplanes and automobiles. And that's what they do. Next page, highlight. Some of the American academics say the main reason for not offering this degree is there's simply no need for it. There are reasons not to do it, mentions this one person at University of California, Davis. He terms designation confusing. Sports engineering is mechanical engineering. Okay, thank you. That's why we're ME majors. It opens so many doors for us. It opens so many doors for mechanical engineers. It's both things rolled into one. Manufacturers sometimes don't know what sports engineering degree means. A degree in mechanical engineering, yeah, they know what that means. Same in biomedical, okay? So, yeah, you can get in sports engineering, of course, with a mechanical engineering degree. That's the beauty of it. And there is just a ton of opportunities, because you know how big sports is across the world, not just in the good old USA, but across the world. Big time stuff. Try and explain this to your friends. Why is a ping pong ball smooth and a golf ball dimple? Same size, roughly. How come? You tell me, you're the engineer. You know it all, you're graduating. Tell me. Well, you know, try and hit this guy off the tee and see how far it goes. Phil Nicholson, okay? It's going to go very far. Hit this thing with a ping pong paddle. See how far it goes. Oh my gosh, you'll break the paddle. This guy's not dimpled. Why? You don't want him to go far. I don't want to go off the table up there, 50 feet away. I want to drop down in 3 feet. Drop down. See, the weight, greatly different. That's sports engineering. Baseball, tennis ball. How come he's smooth on part of it and he's so rough? You're the mechanical engineer. You graduate. You tell me. My degree's in accounting. I don't understand this stuff. Explain it to me simply. I can't do it. I'm sorry. Just have fun, play the game. But yeah, there's a difference there. There's a difference there. This guy is fuzzy. The golf ball's dimpled. The table tennis ball's smooth. How come? Sports engineering. Yeah. This thing here. Okay, there it is. I'm going to tell you. Well, okay. Some pitchers are special pitchers, not many, and they kind of hate to throw it, and the catchers catchers hate the pitchers for this. I can't do it. My fingers won't do it. But they throw a knuckleball. which means the ball is pretty much on your knuckles. The Dodgers had one a year or two ago. Might still be there, I'm not sure. He was a knuckleballer. Boy, that ball behaves so strange. The catchers, they just never know where it's going to go. And when you don't know where it's going to go, you're jumping left, jumping right, jumping up, sprawling flat on your stomach because you don't know where the ball's going. Well, how come? Because if I throw a fastball, I know where it's going to go. I mean, you catcher's glove there, pow, right into the glove. This guy here, you don't know where he's going. Well, you see these red things? Those are called seams. Seams on a baseball. What are they? They're roughness. Oh, there's that magic word again, roughness. So here comes the baseball. Let's assume it doesn't move. Comes in just like that. Okay? Air hits the front. Laminar boundary layer. Hits the seams. Uh-oh. Roughness, like the table, with the boundary layer on the table. Goes turbulent. Okay. The key to throwing a good knuckleball, you can see it on TV. The camera's on, they can get a picture of the ball going to the catcher's mitt. That ball, you can see it, I guarantee it, I've seen it. That ball rotates very slowly towards the catcher. I mean slowly. That's why I throw it with your knuckles, and you don't do this. Move slowly. So guess what this is? It's in the front, it's in the back, it curves like that. It's on the side. So because it transits randomly to turbulence, the force might go left, might go up, the drag might go down. It can go left, it can go right, it can go up, it can go down. Nobody knows because the ball is rotating so slowly that this roughness causes a transition from a laminar boundary layer to a turbulent boundary layer. Why do you it's not legal. Why do you think you might take some dirt in your hand and do that to the ball on one side only? Oh, that's called roughness. You get rid of this is smooth now. You get some roughness on there. You throw that ball, that roughness is going to impact how the boundary layer behaves on the ball's surface. So, yeah, you can explain it to people. And how do you explain it? Oh, you got to have some fluids background or you can't explain it. No, it just doesn't make any sense to you. So, yeah, this thing here explains so much stuff about sports who have spheres as part of the, in the sport, whether it's a table tennis ball, whether it's a golf ball, whether it's a baseball, whether it's a tennis ball, you know, they're all the same way. Soccer ball, they all behave the same way. So yeah, it's big deal for mechanical engineers who are in sports applications. Now, next thing is, this is in your textbook, but I've reproduced, well, I think it is. Most of this is. These are similar to tables in your textbook. They're not exactly the same, but they're similar. 1, 2, 3, 4, 5, 6. 3, 4, 5, 6. There we go. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3. 1, 2, 3. 1, 2, 3, 4, 5. 3, 4, 5. This first page is what I've been talking about anyway, so I don't think that exact picture appears in your textbook, so I photocopied it from a different textbook. Make sure that's 5. One more? Okay. Okay. Okay, so the first page is just what's on the board right now, all right? But now, oh, by the way, before I get off of this, this ties into, might as well start reviewing for the final. What does the drag force on the golf ball depend on? It's a function of the following. I think it's a function of the density of air. Oh, yeah. You think it's a function of density of air? I'll tell you, go to Denver, Colorado with the same hitter playing in LA. I guarantee you the ball goes further. Okay, why? Because the drag force goes down. Why? Because the density changes. Got it. It's a function of density. Viscosity, of course. Matter of fact, they played in Mexico City this past weekend, PGA. Yeah, the ball went further because Mexico City, mile high. Yeah. Golf ball. The diameter. Little d. Little s. Little h. Okay, d. Golf ball diameter. Little d. Dimple diameter if they're circular. H, depth of the dimple into the ball. S, dimple spacing, center to center. Okay, that's a good. If you're an engineer going to do a wind tunnel study, say, okay, I think the drag force is a function of those variables. Here we go, the chapter on pi theorem. How many? 1, 2, 3, 4, 5, 6, 7. Number of pi's equals 7. How many dimensions? I think mass, yeah, mass in there. I think length, yeah, oh, there should be, of course, velocity in there too, u. So you have to add u in there. Time, u in there. So we've got 8 now. 8 minus 3, 5. Okay, you can use the pi theorem. That's okay. You know, I told you last time for the exam, I said, you can use the pi theorem, or maybe you want to use the by observation approach. If things are easily found by observation, then go ahead and do that. I see one right now. It's the Reynolds number. Sure, I just showed you the picture over there. Of course it's a function of that. You know, capital D and little d have the same dimensions. Inches or centimeters, whatever. Okay, so this is pi 1. Pi 2. Little d over big D. I'm going to take little s over big D, pi 3. Okay, good. I chose pi 4. H over D. Let's see, did I use big D? Yeah. Little d? Yeah. S? Yeah. H? Yeah, good, okay. Okay. I need to get FD now. Well, I remember from that chapter that this particular pi parameter is FD over rho V squared D squared. We did that back in that chapter. There they are. 5 pi parameters if you're going to study the effect of dimpling on golf balls. Oh, it's a very difficult thing to do, so you do it one at a time. You might vary this and see the results, then vary this and see the results, and so on. Okay, but now, are they all independent? Well, can I take 2 of them and combine them together and get one up here? What if I take this one and this one, divide this one by this one? So I take pi 3 over pi 4. Little s over d divided by h over d gives me s over h. No, it's not there. They're independent. They're independent. Just as long as you get independent ones, they're okay. If you want to do it by the pi theorem, that's okay. It takes longer, but you'll get similar results, because it depends what you choose as repeating. Okay, so anyway, that's how you analyze this guy if you were going to do that analysis in a wind tunnel, for instance, which of course they do. Then, if we take a look at these figures on here now, let's flip one over. Okay, I'm going to, I think, put that right here. Yeah. In the textbook, you've got the figure for C sub D on smooth cylinders and spheres. You also have table 7.2. Table 7.2. C sub D for 2D objects. And then you've got table 7.3. C sub D for 3D objects. And they're very similar to what I have on the second page of the handout. What kind of bodies do they have there? Rectangular plates, circular cylinders with the axis parallel to the flow, square rods, we did that before. We did many of these things on here, parachutes, cubes, cones. So there's C sub D for all those objects on these tables in the textbook. Some depend on the Reynolds number and some don't. Most of them don't because they're blunt bodies. For rectangular plate, like a billboard, there's different L over B's. L being the length of the, here's the surface. Here's L, here's B, vertical. So it depends on the L over B ratio, what the drag coefficient is on my handout. It's also in your table, in table 7.3. That's a three-dimensional object. Then you go on the right-hand side of this table. A porous parabolic dish, like a radar dish. Of course, that's important. An average person standing, C sub D times A, 9 square feet. Sitting, C sub D times 8, 6 square feet. Crouching, C sub D times A, 2.5 square feet. So what do? Hurricane force winds 110 miles an hour. You're going to stand facing like this? That's okay. Go. You'll be about 5 miles down the road, you know, if you do. You're going to stand like this? No, you're going to crouch down like that. Did you ever see a buffalo in Wyoming in the middle of winter? Do you think they stand broadside to the wind? Look at their face. They've got icicles hanging down because they face the wind. Because how much of your body do you see? Side view of a buffalo, big. Frontal view of a buffalo, small. I mean, you got to make yourself small to reduce that C sub D times A. Empire State Building. Oh, they run studies on C sub D. Of course they do. They put models in wind tunnels and turn the wind tunnel on. 6-car passenger train. Yeah, they do that for Metrolink trains, stuff like that. Oh, bikes are interesting. Upright commuter bike. C sub D 1.1 for 5.5 square feet. Racing bike. C sub D 0.88, frontal area 3.9 square feet. Drafting, one bike behind the other one. C sub D 0.5. Boy, that dropped down fast. Area is still 3.9 square feet. That's why people draft behind race cars, NASCARs. That's why they draft behind racing bikes. Streamline bike, recumbent bicycle. Oh, wow, C sub D 0.12. Yeah. Tractor trailer trucks, all the C sub D is given there. They've studied trees, okay? They've studied trees. Different velocity of the winds, C sub Ds, okay? Dolphins, large birds. We engineers have studied all that stuff, okay? All that stuff. Go to the next page. Cars, C sub D's gone down with time. Way back 1920s, C sub D, 0.8 on the average. 1950, 0.5. 1970, 0.4. 2005, last data for this particular paper, 0.3 and change, 0.32 roughly. But notice how the curve is getting less and less steep. It's approaching like an asymptote. So it's getting harder to get down to lower and lower C sub D's on cars. They've done a lot of streamlining. but it's getting lower and lower advantage with time. There's two kinds of drag that creates situations with trucks and cars. They show a truck here, and there's rolling resistance and there's air resistance. Now, air resistance is this guy over here. That's the air resistance. That's a C sub D. The rolling resistance are the bearings on the tires, the transmission, blah, 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 okay? You can see when you're going slow, the rolling resistance requires the most power. If you're going 5, 10 miles an hour, there's not a lot of air resistance. Most of it's friction. As that truck passes about 60 miles an hour, then the air resistance picks up dramatically because it's the square. The square's parabolic shape. It's the square of the velocity. And so then the air resistance becomes very, very big. Okay? And then they even have run studies on trees with different shaped leaves. That's how much work is done on drag coefficients. Tremendous amount of work on drag coefficients. There's a tree called a tulip tree. They're out here. They're not here, but they're all over Southern California. Their leaves look like this when it's calm, because they want to expose the most of the leaf area to the sun so that they create food for themselves, photosynthesis. But then when the wind picks up, they don't want to come crashing down, so when the wind picks up, those leaves bend over and go together, and they form a beautiful shape like a race car. And the drag coefficient goes down dramatically because of that. And some leaves have multiple small leaves on their stems. They do the same thing. They took pictures of those leaves in wind tunnels. And then they put the C sub D on that back page, the trees with the velocity, okay? So yeah, it's all kinds of stuff like that that goes on that people aren't aware of. And then you go to the last page there, measuring the drag coefficient of a car. So it just tells you how engineers can put a car in a wind tunnel. This is a full-scale test. You put the real car in the wind tunnel, and you crank up the wind tunnel to a certain speed, and you measure the drag force with your instrumentation shown in the picture there. And so you measure in the lab, you measure the drag force with the instrumentation shown here. You get the velocity by a pitot tube. You measure the frontal area of the car, frontal area, looking straight at the car. Density of the air in the wind tunnel, divide by 2. From that, you calculate C sub D, and he does the calculation there. You can see 0.34. So that's how engineers get, one way they get the C sub D for cars. And then, here's another wind tunnel testing. This is a tractor-trailer truck, okay? Tractor-trailer truck. You can put, if you got a big enough wind tunnel, you can put the whole tractor-trailer truck in the wind tunnel. It takes a pretty big wind tunnel though, okay? Pretty big wind tunnel. So, normally you can't do that. So, this was a good review. We've reviewed a little bit there on the pi theorem, dimensionless parameters. Now let's take the wind tunnel testing. Okay, so we're going to assume, I say, you know what? I can't get a wind tunnel that big to test this truck, so I've got to build a model of the truck. And I'm going to build a 1:16 scale model truck. That means every dimension on the model is 1/16 of the actual dimension on the real truck. So the prototype truck length we're going to assume it's pretty close to it, 15.9 meters. That's a typical tractor trailer truck on the road. So model a truck, length 15.9. It's essentially 1 meter. It's about that long, So I try and find a wind tunnel where I can put that truck model in, that long a truck model. Prototype velocity. Of the truck, we're going to assume it's 60 miles an hour. 26.8 meters per second. And we're going to run a wind tunnel test for a model for that truck. Okay. We go back to the chapter on dimensionless parameters and similarity, and we say, okay, I want to run a similarity study on this. Let me think now. What do I want to equate? The Weber number? Is this bubbles or droplets? No. Mach number? I don't think that truck's going to hit Mach 1. No. Okay. Froude number? Is the water submerged halfway up in water in a flood situation? No. It's all in air. All in one fluid, air. You know what it is, Reynolds number, of course. Okay, so you convince yourself you're going to equate the Reynolds number. Okay. So first, equate Reynolds number. All right, so we have Reynolds number of the model equal Reynolds number of the prototype. Rho model, V model, D model over mu of the model. Rho prototype, V prototype, D prototype divided by mu prototype. Okay. Assume model and prototype in air at same temperature and pressure. So I know rho model equal rho prototype. I know mu model equal mu prototype. Okay, same density of air, same viscosity. It's air at 60 degrees Fahrenheit, 20 degrees C, whatever it might be. So that tells me that the velocity of the model in the wind tunnel should be equal to D prototype over D model times the velocity of the prototype. What does D stand for? Not diameter. No, characteristic dimension. Characteristic dimension. I don't really care what it is. It could be the truck length. It could be the truck height. Everything is scaled to 1 to 16. Doesn't matter what it is. I know the scale ratio. So prototype, 16 to 1. V prototype, 26.8. 429 meters per second, which is very nice little 960 miles an hour. So you crank the wind tunnel up to 960 miles an hour. The Mach number, V over C, air, 1.4 for K. R for air, back of the book. Temperature of air, absolute. Mach number, 1.24. Supersonic. No, I don't want that. I don't want to put that model of wind tunnel where the velocity of the air is almost 1,000 miles an hour. Oh man, no, absolutely not. My wind tunnel is the subsonic wind tunnel. My wind tunnel maximum Mach number is 0.6, subsonic wind tunnel. So you say, oh, geez, you know, that's not going to work. There's no way I can do a model study on that tractor trailer truck because I can't do that. Unreasonable. Max us for a subsonic wind tunnel. The max speed is somewhere on the order 70 meters per second, which is 156 miles an hour. Which is a Mach number of about 0.2. So no, I can't use this. I don't want to get a supersonic wind tunnel, 960 miles per hour. So I say, well, nice try, but I guess I can't model the truck. I guess I can't model it. Yeah, they do. They do. Here's what they do. They take a lot of data. Reynolds number, the C sub D. They take a lot of data at, here's the maximum wind tunnel, max wind tunnel speed. Which is that subsonic wind tunnel. So they start taking data at different Reynolds numbers, and they go in the lab and they take data, and it looks like this. They say, wow, that curve's interesting. It drops really fast, and then it kind of seems to level off. You know what I'm going to do? I'm going to assume it levels off. It's dangerous sometimes, and they've proven this to be true, though. I'm going to assume it stays level this whole way out. Now, if you do it over here, you're in deep trouble. You say, well, it leveled off at 0.5, so I'm going to assume, no, you're going to be really, really, really wrong. Here, they've proven that you can be correct most of the time. So where is my based on V model? Okay. So here's the Reynolds number. This is based on V model, okay? See, I can't get to 960. I can't get to that Reynolds number. That's a really, really big Reynolds number. I don't care. Here's what they say. We're going to assume that C sub D stays the same because it goes flat down here, and I don't think anything's going to change it. So my best guess is that that's the value of C sub D that we can use. So that's how they get around that large velocity that creates a large Reynolds number. They take data within the range of the wind tunnel's velocity, and most of the time, this is for cars too, most of the time they find that it flattens out at a certain Reynolds number, and it kind of stays flat beyond that. So then they say, well, we can't match the Reynolds number, but that's okay because C sub D didn't change between those two Reynolds numbers. That's the game we play. And then you can see the picture there on that page. It shows it down there at the bottom, okay? And it's, if all else fails, we could run the wind tunnel at several speeds near the maximum speed and then extrapolate our results to the full-scale Reynolds number. Run a lot of tests near the maximum speed, where it flattens off, assume at that Reynolds number, that's the same C sub D. Or if you want, put the whole truck in the wind tunnel. There's a picture right there. The whole truck is in a wind tunnel. I told you they test funny cars in wind tunnels too, NHRA. They put the whole car in a wind tunnel. It's got to be a big wind tunnel though. You know, if you put it in the real car, what's your scale? 1 to 1. If you put the real thing in a wind tunnel, what's that? 1 divided by 1. What's your speed? 60 miles an hour. Oh, I can handle that. My wind tunnel goes up 156 miles an hour. So you want to put the real car, the real truck, in a full-size wind tunnel? You can do it if you can afford and find a big enough wind tunnel. Yeah, you can do it, but most of the time we do model studies. We make things smaller than the real thing and then use these similarity studies to determine what the, for instance, drag coefficient is, whatever it might be. You can model the whole Manhattan, New York City, Hudson River, where all the ship piers are. You can model that. They do. They over a floor bigger than this, and they put water in there, and the water goes down the floor, and then the piers stick out of Manhattan. So here's Manhattan, and here are all these shipping piers, and here's the Hudson River, and they model that on the floor in a hydraulics lab, civil engineering. And you're going to find out that there's swirling here because it's roughness. And this is where all kinds of sand and debris gets deposited, which means the ships have a tough time to enter that area and dock. And of course, that's a big worry. You don't want your ship hitting sandbar in there. So they do studies to see how bad the problem is and how to alleviate the problem. Okay, so model studies are just done on everything. Not just what we're talking about here. Then I think that was the last on that. Let me just make sure we got all that covered there. Yeah, we did. Okay. Yeah. Well, we'll go back. Tractor, trailer to truck. Okay, that's what this is. We'll put it over here. Standard. So here's the truck. Okay, let's see the picture. There's our picture. So here's the picture of the truck. And of course you've got the, that's a trailer. And then you've got the cab here. And C sub D 0.96. How'd you get that? You put a model in the wind tunnel and tested it like I just showed you. Then they add a fairing to the top. These things are all over trucks nowadays. They're stuck on the top of the cab like that. Ooh, thank you very much. My C sub D now drops down to 0.76. You think that'll save gas? You better believe it will. Diesel fuel? Uh-huh. Uh-huh. Now you put a fairing and a gap seal. This is called a fairing up here. A fairing and a gap seal. So they extend the cab with a piece of metal here. On each side of the cab, there's a piece of metal. Look on the highway, you'll see them. C sub D. Wow. 26% reduction. Boy, do I get better gas mileage now on the interstates, highways. Yeah, uh-huh. That's what they do. You'll see them all over the place now. They put this skirt on it down here. Oh yeah, that skirt on it. That's not to make it look pretty, believe me. No. What does this fairing do? Look from the top. Here's the top view. Here's the truck body. Top view. Here comes the air. Now, problem is, let's do two things here. I'll do this I'll come back to that. Okay. See, we engineers are always thinking, how can we reduce the drag to increase the gas mileage on these guys? Okay, here it is. Air comes up here, goes around here. Oh, that's not good. That's like putting a billboard in the wind. Bam! Air hits that, tremendous drag. Put the fairing on it. Ooh, that's smooth. That's what they do. Cuts the drag down by what? Oh, roughly 20%, a little less than that. Now, top view. So here's the front. Here's the body. Truck's going 60 miles an hour or more anyway. There's a slight wind from the east. So here comes the wind. It hits this, goes along there. It hits this, it goes around there. Here's the problem. It hits this, oh my gosh, that's trouble. That's trouble. The air goes between the cab and the truck trailer. Not good. So what do? They put the fairing on it. What is the fairing? It's a piece of sheet metal stuck on it like that. What's the purpose of that guy? That's the purpose of it. Push the air back that way. 0.7 now. It depends on the wind direction. Worst case scenario is, wind's that way. Then most of the air would go right through here. Cut it off. Make it go that way. You don't want it cutting through between the trailer and the cab. Now, from the top, the wind comes in. Here it comes in this direction. I got it showing here. It hits the side over here. It hits here. The top body of the trailer, it's going to go there. But on the bottom, there's a way it's going to get around there. It goes under the body of the trailer. No, I don't want that. That creates drag. So what do? I put skirts on both sides. Every truck has them now on the 10 and the 60. Look at them, you'll see them. The skirts, they cut down. Is it worth it? Oh, you better believe it's worth it. This pays off in months. This pays off in months. This pays off in months. Their diesel fuel bill goes down dramatically. Yeah, it's worth it because they all have them. Look at them now. They all have them. Some students from a college in the past have done this for a senior project. And they said, the back of the truck is a problem. The back of the truck's a problem because when the air comes off of here, it creates this huge region of a wake region, which creates a drag. So these students, for their senior project, they were ME students. From the top of the truck, they built this clamshell door here, okay, to help the air go around the truck like that. And then when you're ready to unload the truck, there's hinges here. So the clamshell goes out of the way and you unload the truck. Okay, that was their senior project. I won't mention the school, but they probably know if they see my video who it is. They took that truck, it was a bobtail truck. They took the truck to test their senior project to the high desert where they had long stretch of straight road. They waited for a very calm day. They took it off of the back of the truck. They ran the truck, okay? They got gas mileage. They put the doors back on the truck. They ran the truck. Better gas mileage. I don't know if it was 10 or 20%, I forget. But it never got to be popular because it's kind of hard to do for, truck drivers and people that unload and load trucks to have those doors that swing open like that to load and unload the truck. But anyway, the whole problem is get rid of that wake region by doing something like that. And it was a neat little senior project, 3 students from that particular school, okay? Even here at Cal Poly. Even here at Cal Poly. The technology department. There it is. Technology department. They built it. Senior project. Model of a truck. Mirrors, steps, lights, rivets. I can feel them. Rivets. Yeah. They put, oh, there's a skirt. Down there's a skirt. They didn't put, there's the fairing on the top. Yeah, they put little wings on the side. I can put my finger in there. They put the fairing, so this is the fairing that goes on the side. Here's the skirt on the bottom. Here's the cab fairing. And I told you there was a wind tunnel down in the fluids hydraulics lab. And these technology students built this thing. And then they put it in that wind tunnel. And they just wanted to see the smoke lines around here. So they, up here where the wind comes from, this way, they dropped oil onto a hot wire to create smoke. And they watched the smoke go across here and how the smoke patterns work, took pictures at various Reynolds numbers in there to see how that changed that. Not them, but other people that studied trucks said one of the biggest contributors to drag on a truck, believe it or not, are all these mirrors on the cab. Some of them have 3 mirrors on the cabs. 3 mirrors, I've seen them. That stuff sticks out like a billboard, like this. Stop, air, no, no. So they said one of the biggest contributors to drag on a truck are the mirrors on both sides of the cab of the truck. I'm sure this thing here is also a big contributor. That's not good. It helps you to see on sunny days, but that's not a good thing to put on a truck. So yeah, you can do stuff like this. It's just kind of neat stuff to do. Okay, that's good for today. We're going to stop. We'll get together then on Wednesday and do some final exam review then.